Okay guys, thanks for bearing with me through the course of this series of videos. We have two more examples to take a look at, finding the volume of the figures. And I strongly encourage you at this point, if you haven't done so, please try pausing the video and see if you can work the videos out or work the examples out beforehand, and then maybe hit play to see how I am going to work them out. But let's go ahead and take a look at this example here. Example 7 says find the volume of a solid generated when we have a function 1/2 plus x squared and g of x is equal to x over the interval 0 to 2 revolved about the x-axis. So a couple things straight away that we notice is that the interval is identified for us. And because we're revolving it about the x-axis, if it wasn't already, we would make sure that we wanted to solve our equations for y. Okay, so we don't want to mess with any of those things there. Now we do need to sketch the regions so we can correctly identify our interior and exterior radii. So I'm going to go ahead and do the quadratic here in black. And we're not going to try and make these to scale necessarily, but the quadratic is just the parent function shifted up half of a space. So it's going to do, and I think I'm making that a little too wide, even though I'm just generalizing. So we're going to have something like that. And then the line, the linear parent function g of x, let's go ahead and do that one here in this kind of greenish color. That's going to go like that. And yeah, I'm really kind of off, I think, on my parabola. I think I'm going a little too wide. Let me go ahead and fix that just a tiny bit. And just so we can see the region a little better. So we're going on this one from 0 to 2, and because we're doing it on the, we're revolving it around the x-axis, that is where the interval is going to be from 0 to 2. Now the region that we're going to be looking for essentially is going to be kind of in between these two bits here. And now that we have the function sketched, we can identify what our interior and our exterior radius is going to be. Okay, so let's do the interior radius first. And we're doing it from the x-axis. And let's pick a different color in green. So I'm going from the x-axis. Okay, so that means this function here that was in green, that is the interior radius, the small r, and I can't get a parenthesis there, and the exterior radius, let's do that one kind of in this, let's do yellow. The exterior radius, because we're revolving it around the x-axis, okay, the exterior radius is going to be the quadratic. Radius, the capital R, okay? And because both of those, you know, the function notation, obviously f of x, g of x, but essentially they're already solved in terms of y, we can go ahead and just start plugging these things in. So let me pick a little bit darker color so it's easier to see the work here. So the volume, there we go, in this case is going to be pi times the definite integral from 0 to 2. And the first one that we're going to plug in is going to be the quadratic. And I'm going to rewrite the quadratic kind of in standard form. So I'm going to say x squared plus 1/2. And we have to square that because that's the radius. And now we're going to subtract the interior radius, which is the linear function. So I'm going to say x squared, and the height is going to be the change in x, so that's the dx that represents the height. So volume is still equal to pi r squared times height, but the r squareds are going to be where our integration is taking place. Now, moving on, let's go ahead and simplify the integrand. So 0 to 2. So we're going to expand the binomial, and that will give me x to the fourth plus 1x squared, and that fourth looks like a d fourth, plus x 1x squared, and then plus 1/4, and then we're going to wind up squaring the x, so I'm going to get a minus x squared, all of it times dx. And you can see that the x squareds in the integrand are going to cancel each other out to make 0. So we have 0 to 2 for our interval, and we're going to be left with x to the fourth plus 1/4 times all of it times dx. So we've simplified our let's back up. We've simplified the integrand, and it can't get any more simple than what it is now. So at this point, it is time to do the antiderivative and get rid of the integral symbol. So we have pi. So the antiderivative of x to the fourth will be 1/5 x to the fifth power. And the 1 to the fourth, so that's going to be 1 over 2. So that'll be plus 1/8. Nope, nope, nope. For some reason, I'm thinking that it already has an x on it, and it absolutely doesn't. So this is just 1/4 x. And we're evaluating it from 0 to 2. And my 2's are not coming out very nicely, but I hope you understand that's what it is. My pen does not like to work with my computer very well. And now we'll go ahead and follow through with fundamental theorem of calculus stuff and do our plugging and chugging at this point. And again, the 1/5 and the 1/4 need to stay inside of the bracket or the parentheses because they're not going to be the same constant or the same coefficient, so we can't factor it out. So I'm going to wind up with 1/5 times 2 to the fifth power plus 1/4 times 2. And if we substituted the 0, everything when we substitute the 0 is just going to simplify to be 0. So I'll just say minus 0. You don't have to write it, but and now, pardon me, keep going. Sorry, my throat's drying out here. So that's going to give us what, 32? 2 to the fifth power is 32. So we have 32 fifths and plus 1/2. So the common denominator there is going to be a 10. So 64 and 5 is going to give me, volume is going to be pi times 69 tenths. So volume of this particular shape will be 69 pi over 10. Oh, go. What did I do? What did I do? There we go. Go. There we go. Okay. I'm going to pause the video and fix whatever I just did before I go on to the next one. For you guys, it won't be a second, but. Okay, so now we've completed that example. Let's go ahead and take a look at our last one here. And the example here says drill a hole through a metal spear with a radius of 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Now again, this one is something that you could very easily do if you remember the formula for volume of a sphere. But we're going to go ahead and just kind of stick with the calculus stuff for it here. And let's see. So I've given myself a compass here to kind of make a circle with, because there's no way I'm going to be able to draw a circle even remotely like what I would like it to be. Oh, and you need to kind of open up, and so we'll just say that this is 5. Whatever that is, we'll just say that that's 5 inches. So, oh, there we go. So there's 5 inches. And so now we're going to kind of close it up a little bit. We'll just say that here is 3 inches. And let's see, can I pick a different color on that? Maybe, hopefully. There we go. Let's do something a little bit more, that has a little bit more contrast to it. And so here is what we're kind of drilling out. So imagine this is a sphere. I know it's not a, these are just two-dimensional circles, but imagine, it's a sphere, and we can go ahead and oh, there we go. That's what I want to look at. There, go away. Okay, so we have our circles, and we can very clearly see that the interior radius, the darker circle, is 3 inches. The greenish looking one is the exterior radius, the 5 inches. And they're giving us here the equation of our circle. In this case, they're not giving it to us, but the equation of the circle is going to be pretty easy to do with a radius of 5 inches. So that would be, let me go back to that kind of that greenish color, I guess. There we go. So we're going to have the equation of a circle. The outer circle would be x squared plus y squared would be equal to 5 squared, or 25. And the radius of the equation of the inner circle, should we need it, will be x squared plus y squared equals 3 squared, or 9. Okay, so let's go ahead and identify what the interval is going to be. So the interval, as, let's see, what is the volume of the resulting ring? It doesn't really say which one that we're going to revolve it around. Drill a hole through a metal sphere, radius 5 inches. So we'll just go ahead and say, let's go ahead and revolve it around the x-axis. Okay, so let's revolve it around the x-axis. And so this bit right here is going to be your interior radius, and this bit right here is going to be your exterior radius. So r and little r here. And the interval is going to be, well, where do they intersect each other at? Okay, so at 3, what we're doing at 3 inches, so we have our sphere, and let me go ahead and pick a color here. We have our sphere, and we're going to drill a hole in it, like here and here. So this is, all of this is our, let me maybe not do all of that in black. There's our hole. Let's kind of pick a highlighter here. So all of this stuff here is where the hole is going to be. Okay, and so what I want to know for the interval on the x-axis is where are those horizontal segments going to intersect the exterior circle? Well, this here, we know that from here to here, this is the equation. Because the radius is 3, this horizontal line has to be y is equal to a positive 3. So this horizontal line here would have to be y is equal to a negative 3. And seeing when y is 3, if I were to take that and solve the circle, where would I be on the circle? That point right there is going to be at positive 4, positive 3. And so this point right here, due to the symmetrical nature, is going to be at negative 4, positive 3. So if I'm revolving it around the x-axis, the interval is going to be along the x-axis. So the interval, in this case, I'm going to say will be from, you can say that the interval will be from negative 4 to positive 4, or you could say it's going to be from 0 to 4 and double your interval, or double your volume essentially, by using the symmetrical nature of the circle. Okay. So let's go ahead and start working this out. Let's see what our equations are going to be. So if I solve the equations, so the radius is perpendicular to the x-axis, so I want to find the radius in terms of y. So let's solve our equations in terms of y. Now the little radius is easy enough to figure out. The little radius, the interior radius, is going to be 3. So let's just go ahead and put a 3 here for the interior radius. And the exterior radius is going to, we have to take the equation of the circle, the big circle, and solve it for y. So if I do that, I'm going to get y is equal to the square root of 25 minus x squared. Okay? And so now we have our interior and our exterior regions, and let's go ahead and do our integration. Now, personally, I kind of like the lower bound of the interval to be a 0. So I'm going to go ahead and look at it with this one here, and I'm going to uh, double my volume here. And so the way that I'm going to do that is I'm going to say that the volume, oh, let me go ahead and pick a different color here. Let's go ahead and use red. I don't think I've used red yet. So I'm going to say volume is going to be equal to 2 pi 0 to 4. And so the interior, the exterior radius in this case is going to be, and this should just be a parenthesis. My hand keeps hitting things. I apologize for all these things kind of popping up, but this will be the square root of 25 minus x squared, and then minus 3 squared, and that will be the height of the cylinders that we would be looking at, or the washers that we would get, in this case, are going to be dx, the change in x. So let's go ahead and see what we get. So here I'm going to have 2 pi, definite integral, 0 to 4. And when I square the first parentheses, that's just going to give me 25 minus x squared. And then we're going to say minus 9 dx. And so simplifying just a little bit more, we will get our integral to be 16 minus x squared. And at this point, we can take the interval, or the antiderivative, I should say. So I'm going to say 2 pi, and The antiderivative of 16 is going to be 16x, and the antiderivative of the x squared is going to be minus 1/3 x cubed. And in this case, I'm going to be evaluating it from 0 to +4. And at this point here, we just kind of let our plug and chug kind of stuff take over. So here we're going to say 2 pi, and we're going to get 16 times 4 minus 1/3 times 4 cubed. And if we substitute the 0 for the lower bound, all of that's going to just simplify to be a 0. Okay, and so now we're going to get, and I don't see, let's see, 16 times 6, or 16 times 4 should be a 64, and 4 cubed is going to be, let me just double check. I want to say it's 64 again. Yes, yeah, it will be 64. So that'll be minus 64 over 3. And I'm running out of space here. Let's just keep moving down a little bit. So volume will be equal to 2 pi. So 64 minus 64 thirds. That'll be 128. Yes, 128 over 3. And if you multiply 128 by 2 pi, that will give you a volume of 256 pi over 3. In this case, they gave us our dimensions, so we have to include them as in our answer, inches cubed. And that will conclude the presentations that we have for volume of three-dimensional objects using the disk and or the washer method. I appreciate your patience and I hope everybody is doing well. Thank you for watching and take care.